Hello! Today we are doing logarithms. Now, a logarithm is a new vocabulary word. Logarithms are basically ways to express an exponent. So, a logarithm actually represents an exponent. So, you kind of have to think about this in those terms. So let's talk about it. So if I solve this equation, this is an easy one, 2x equals 8. We're going to divide both sides by 2, and x equals 4. Or if you were thinking in your mind, what times 2 gives me 8? Well, that's pretty easy. 2 times 4 is 8. Now we're looking over at this one, and this is 2 to the x is 8. So you might be asking yourself, okay, what is x? Well, x is it represents our exponent, right? X is an exponent. We call 2 the base of that exponent. And I need to know 2 to what power is 8. So the question I'm asking myself is 2 to what power is 8? Well, if you think about it, you should know that 2 to the third is 8. So in this case, x is 3. I don't know why I wrote 8. We're going to say 3. X is 3. This expression right here can be written as a logarithm. The inverse of that expression is called a logarithm. So the logarithm of base b of x is defined as log base b of x equals y. If and only if b to the y equals x. So if we go back to this 2 to the x equals 8, we could rewrite that as log base 2 of 8 equals x. And again, this is something that you can type directly into your calculator. B cannot be 1, obviously, because if b is 1, then x is just 1. And x has to be greater than 0. So exponents, in this case, have to be greater than 0. Because, or not the exponent, yeah. You can't have anything that's negative when you use an exponent. They're outside. You can't have anything negative over here after you've applied the exponent. So the logarithmic function, y equals log base b to the x is the inverse of the exponential function. So if you think about, if you have y equals b to the x, and we're looking at growth here, we know that it looks like this. So it starts out flat and gets really steep. Well, the inverse of that is going to start out steep and get really flat. So that's what that inverse looks like. Okay, let's go on to example 2 now and see this. Let's practice converting. So the converting of these is, okay, so we've got 3 to the 4 equals 81. So this is our b. This is our x. Whoops, I'm going to put that in a different color. This is our x. And that 4 is our y. So the way that we would write this is, that is not the color I wanted to use. I'm trying to color code this for you guys. 4 is our y. So we're going to have log base b of x equals, and then we put our 4 over here. So our exponent. Then if we do the exponential form of log base 10 of 1,000. Now, what you need to know is that log base 10 is called the common log. So when you see log base 10, this is called the common log. And we typically just don't even write the 10. So if you just see log of 1,000 like that, it means the same thing as this. So again, though, we're going to write that as, I'm going to write it down here and color code it for you, log base 10 of 1,000 equals 3. Now you'll know how to write this, right? So we're going to write it as 10 to the third equals 1,000. Not 10,000. Whoops, 1,000. So that's how we convert. So now question 3 asks us, what's the value of each logarithmic expression? Sometimes it's really easy to see. Sometimes you need to just put it in your calculator. So this is 5 to the x equals 125. Well, if I put this in my calculator, it should give me 3. 1/4 to the what power is 16? Well, this is a fraction, so I'm going to have to flip my fraction to get an inverse. I'm going to have a negative number here. And again, if you put that straight into your calculator, you're going to get -2. Now, this one, if we rewrite this, we get 3 to the x equals 0. Well, when can 3 to any power ever equal 0? And the answer is never. Because if you think about your powers of 3, 3 to the 0 is 1. 3 to the first is 3. And then if we back it up and do 3 to the -1, that's -1/3. Or, that's 1/3. Woo! We're never going to get a negative number in there. And if you'll remember that I wrote that wrong, you guys. I'm sorry. Because the way that we would write this is 0 to the x equals 3. And that is never going to happen either. So this one is undefined. But by that same token, if we had log base 3 of 0, that is what I was talking about before. And that's 3 to the x equals 0. And that is also undefined. Because we're never going to get a 0 out no matter what our exponent is. Now, look at this one. This is 2 to the x equals 2 to the 8th. Well, that's easy. 2 to what power is going to be 2 to the 8th power? Well, in this case, x equals 8. So what we say here is that when you have your base and it's equal to whatever's here, when a equals c, then they cancel. The log cancels. And you're just left with that exponent. Then your exponent equals your exponent. So in this case, 2 to the 8th is 8. So that's how we get there. Okay, example 4 says, what's the value of each logarithmic expression to the nearest 10,000th? So again, here you're just going to use your calculator, and it can be Desmos, it can be your TI Inspire, it can be whatever you want. But just so we know what this means, we have 10 to the x equals 900. Well, that's not going to be something pretty, because it's going to be, let's use a little logic here. So 10 to the first is 10. 10 to the second is 100, and 10 to the third is 1,000. So it's obviously going to be a number, x is going to be between, it's going to be bigger than 2, but less than 3. And it's probably going to be a little bit closer to 3. So if I put this in my calculator, exactly how it appears, it's going to spit out 2.9542. And we're taking it to the 10,000th, which means 4 decimal places. So tenths, this is tenths, hundredths, thousandths, 10,000ths. Okay, ln of e. Okay, when you see ln ln is the same as log base e. That's how, but log e looks like a loogie, so we don't use that. So we call ln the natural log. And so if you have the log base e of e, guess what? Those e's cancel. Well, that e and the whole log base e cancels, so we just get 1. So when you see ln of e, that is just 1. And then finally, if we think about this, we're going to have e to the what number is going to give us negative 1.87. And we've already talked about this exponent up here is never going to consistently give us a negative number. And the reason being, let's explore this whole negative thing. I'll tell you that this one's undefined and you're going to get an error message in your calculator. But let's talk about this just a little bit more in depth. When you have a number, so even a negative number, raised to any power. So if we talk about negative 3 to the x, if x is 1, then that's going to be negative 3, right? But if x is 2, then we're getting a positive 9. If x is 3, we're getting a negative 27. Ooh, sorry, negative 27. So these skip back between negative, positive, negative, positive. So it's never consistent. That's why your number in here can never be negative. It has to be not only positive, but it can't be 0 either. So it has to be positive. All right, example 5. Now we're going to solve equations. So we need to look at what these look like. So here, 10 is our base. So that means that we're going to use our common log 10. It's equal to 25. So log base 10 of 25 equals x minus 1. So then we're going to have log of 25 plus 1 equals x. And again, we just throw that in a calculator. Don't you love these? I love it when we can do stuff in a calculator. Now here, we know that that's our base down there. So we're going to say e to the 4th, because this is our exponent over here, e to the 4th, equals 2x plus 3. So we're going to do e to the 4th minus 3 equals 2x. And then we divide everything by 2, because we added 3 first, plus 3. So those cancel. And we get 2x equals e to the 4th minus 3. I don't know why I put plus. It's because I know you guys can read my mind. That's it. Okay, now this, once we get to this point, those are all represent numbers. So we can just throw that in the calculator. When we throw it in the calculator, I'll actually give you the number for this one. We're going to get 25.799 is approximately x, because again, we're rounding. And this one we're going to the thousandths. So tenths, hundredths, thousandths, 3 decimal places. Okay, finally, we're going to use a log in a word problem. The seismic energy x in joules can be estimated based on the magnitude of the earthquake by this formula. What is the magnitude of an earthquake? So we're going to replace x with m with seismic energy of 4.2 times 10 to the 20th. So our magnitude, this is our m. So we're going to have 4.2 times 10 to the 20th equals 10 to the 1.5 m plus 12. So we've got to get that m right there by itself. There's our number that we are trying to get alone. So what we're going to do is we're going to take the log and we're going to do the common log, because this is our base right here. This is our b. So we're going to say the log of 4.2 times 10 to the 20th is 1.5 m plus 12. So I'm going to put this in my calculator. Well, I'm going to subtract 12 from both sides first. And I'm going to come down below this little thing to get that a little bit better. So we're going to have log of 4.2 times 10 to the 20th minus 12 equals 1.5 we divide by 1.5 and divide by 1.5. Now notice that on this I am not typing enter after everything. You want to be able to enter these into your calculators exactly, and I'll show you guys again on Desmos when we are in class a little bit more accurately how to do this. So what we're going to do is we're going to get that m is all of this entered into my calculator, which gives me approximately 5.75. So the magnitude of this earthquake is 5.75. Logarithms and exponents are basically inverses of one another, and you should be very comfortable switching back and forth between each one. And we'll do lots of practice with this in class. You all